So, dear students, so far we have studied the basic notions of category in our first three lectures, where we discussed some of the examples of categories, including those having objects as structured sets and morphisms as structure preserving maps. We also studied certain categories where objects are not necessarily sets and morphisms are not necessarily functions. Now, in this lecture, we want to add some more examples of categories. So, first, we want to discuss finite categories. So, finite categories. So, what are finite categories? So, a category C is said to be finite. So, given a category C, C is finite if object of C has finite number of objects. So, objects of C are finite, and between any two distinct or same pair of objects A comma B, this home set of AB is finite, is a finite set. Okay, so these categories are called as finite categories. So finite categories can be constructed very naturally, in the sense that given any object, you can regard this as a category. Even a single object can be thought of as a category. So this category is denoted by the symbol 1. So the beauty of category theory is that even a single object can be thought of as a category. So the category so I call this category 1, simply 1, denoted by this, and is as follows. So it looks like so it has only one object, so I call this object as, say, star. So it's a category. It has only one object and its identity arrow. Okay, so objects of this category is simply star, and arrows are what? Only identity of star. So it is trivially a category. Now, any two distinct objects can be thought of as a category. So this is the second example. Suppose I have given two objects. So I call one object as star and other object I call star circled. Okay, so this category is called as the category of only two objects. So I call it 2. This is the name of this category. Here 1 is the name of this category, 1. 2 is the name of this category consisting of two objects, star and star circle. Okay, so it looks like this, and there is exactly one arrow from star to star circle. So it has two objects, the required identity arrows on star and star circle, and only one arrow from star to star circle. So it has two objects. The identity arrows on each object, the identity arrows on each object, and exactly one arrow between the objects, and exactly one arrow between the objects. between the objects. So it is trivially a category because there is one arrow. So you compose this arrow. Say this arrow is F. So you compose this arrow F with identity on this star. You would get F, and identity on star circle composed with F. Again, you would get F, and the composition is trivially associative. So this forms a category. Now you can go on extending the number of objects. So suppose I have now 3 objects. So suppose I have an object, I call it star. The other object I take again star circle, and third object I take this big dot. So this category is called as category 3, consisting of 3 objects. So example 3, so the category 3 looks like the category, so I call this category as 3. The name of this category is 3. It looks like this. So there is exactly one arrow from star to star circle, and exactly one arrow from star circle to this big dot, and then their composite. So say if this arrow is F, this arrow is G, and then this arrow would be G after F, or G composed with F. So it has 3 objects. The required identity arrows on each object, and exactly one arrow from first object to second object, exactly one arrow from second object to third object, and exactly one arrow from first object to third object, and that is nothing but the composition of these 2 arrows. Okay, so in this way it forms a category. Category axioms are trivial because G composed F applied on this identity on this, you would get again G composed F, and similarly identity on each object composed with these arrows would give you these arrows, and associativity of arrows is also trivial. So it is trivially a category. So what are finite categories actually? Finite categories you can construct by yourself simply by taking some arrows, and so it is easy to specify finite categories. Just take some objects and start putting arrows between them. Make sure to put the necessary identities and composites as required in the data of a category, and composites must be associated. Say for example I have 4 objects and I want to see the category 4. Similarly I can put the arrows and put the necessary composites so that it becomes a category. Say for example I have this arrow, this object, I call it A. I have another object, I call it B. Another object, I call it C. Another object. So 4 objects I want to take. So I want to make it as a category. So simple. So I put an arrow from A to B. I call it F. I put an arrow from B to C. I call it G. So once I have put these arrows F and G, now I have to make sure that their composite must exist. So I just take this arrow, I call it G composed F. Okay. Now I again put an arrow from these 2 objects, from D to C. I call it K. So now I can put an arrow from A to D. Say this arrow is H. So once I put these K and H, so I must assure that their composite. So what do I do here? I put the composite of H and K here. So I call it K composition H. Again, I assume that identities on all of these objects, they exist. So identities are assumed. Identities are assumed. So I am able to construct a category of 4 objects. You can trivially verify that these axioms of category, they are satisfied. So this category is what? This category is called as 4. 4. Okay. Category of 4 objects. Now in a similar fashion, you can construct finite categories. But we have to make sure that we must put necessary composites and identities, and also ensure that the composition, wherever it is defined, must be associative. Now, suppose I have this type of situation. Suppose I want to highlight one more thing. So another example. Suppose I have a situation like this. I have given 2 objects, A and B. So I have an arrow from A to B, that is F, and I have an arrow from B to A, an arrow going in the reverse direction. I call it G. So even though here we have 2 objects, and apparently it looks that there are 2 morphisms, 2 arrows, F and G. But until and unless I assume that G composition F is identity on A, this category won't be a finite category. Even though it is a category, but it won't be a finite category, because I can go on taking the compositions in this fashion. G composed with F, G composed with F, composed with G composed with F, and so on. So in this way, I will end up with infinitely many arrows. So there would be infinitely many arrows. Infinitely many arrows in this category. Even though there are 2 objects, but arrows would be infinitely many. So this won't be a finite category. But if we put the condition that G composition F is the identity arrow on A, then it would be a finite category, because then it would have finitely many morphisms or arrows. So this is how we can construct finite categories. Now I would give another interesting example from logic. So what is this category? It is the category of proofs. So category of proofs. Category of proofs. So suppose I have a deductive system of logic. So I hope you have little bit knowledge of logic. So deductive logic, it is that system of logic where we deduce formulas from certain axioms or hypotheses. So there are 2 types of logics. One is deductive logic and other is inductive logic. So in deductive logic, we come from general to particular. Means there are some axioms, so we prove particular statements. And in inductive, we go the other way around, from particular to general. So what is deductive logic? It is the concept or the logic of deducing, or you can say proving theorems or statements, or you can say formulas. You can also say statements. So the concept of deducing or proving theorems, formulas, or statements from set of axioms, from a finite set of axioms or set of axioms. So these axioms are given, and rules. Axioms and rules of inference. So we make certain assumptions and axioms. Based on those axioms, we prove statements, or you can say we prove formulas or theorems. So such logic, such system of logic is called as deductive system of logic. So in this system of logic, we have an associated category, that is the category of proofs. So what is this category actually? The objects of this category are formulas or theorems or statements. So objects of this category are, you can say, formulas, or you can also say they are theorems or statements or whatever. Okay, so say these are denoted by phi, psi, lambda, and so on so forth. And what is an arrow? What are the arrows here? So suppose I have two formulas or statements as objects, so say phi and psi. So I have an arrow p from phi to psi, and what is this p? P is the deduction of psi from the assumption phi, where p is the deduction of psi from the assumption of phi. So what is p? P is actually the proof. Okay, so the proof of the statement psi by assuming the statement phi. Okay, so the home set of phi and psi is what? Proofs of, you can say, proofs of psi by assuming phi. Alternatively, you can also say that p is what? P is nothing but phi implies psi. Okay, so the p is the proof of the formula psi by assuming phi. So p is what? You can say that symbolically p is the statement phi implies the statement psi. So this home phi psi is not necessarily a singleton set, because there can be many proofs of psi, more than one proof of psi by assuming phi. Okay, now composition of arrows here is what? So composition. So suppose I have, say, phi, psi, and say a formula or statement lambda. So suppose p is an arrow from phi to psi, and q is an arrow from psi to lambda. Then so p implies q, sorry, p is what? Phi implies psi, and q is psi implies lambda. So once phi implies psi implies lambda, then phi also implies lambda. So I can take the composition R, where R is what? The proof of this lambda by assuming psi. So R is what? R is what? R is phi implies lambda, and I call it this R as Q composed with P. Okay, and what is the identities? So identity on phi is what? So phi can be trivially proved by assuming phi. So it is trivially proving phi by assuming phi. Okay. So or you can say identity on phi is what? Phi implies phi. So the trivial case. Now you can easily verify that the axioms of category they are satisfied. Say for example I want to prove the associativity. So suppose I have from phi to psi, so associativity. Now suppose phi to psi I have p, psi to lambda I have q, and lambda to say delta, the arrow is s. Then I have the composite here, that is q composite p, and then I have this composite also, say it is s composite, this would be s composite q. Then it is trivial or straightforward that s composed with q composed with p is same as s composed with q composed with p. Because what is s composed with q composed with p? It is actually phi implies lambda, lambda implies delta. So it is same as phi implies psi, psi implies delta. Okay. So it is trivial. And what is the composition of identity with any other arrow? So identity on phi is phi implies phi. So phi implies phi and phi implies psi. This means phi implies psi. Phi implies psi. So in other words, you can say that so phi implies psi is actually p, and phi implies phi is identity on phi. So you can say that p composed with identity on phi is p. Okay. Similarly, the other way around, I can check the identity. Composition with identity is the same arrow. So this was an example from logic, the category of proofs. So I would also like to add one example from computer science, because in the beginning I said that this category theory has a lot of applications in computer science. So in particular in programming, functional programming. So I would give an example of a category of programming language. Okay, so I have an example from computer science. Example from computer science. Computer science. So again, I assume that you must have or you might have a little bit knowledge of computer programming. Suppose I have given a functional programming L. So given a functional programming language L, I can associate a category to this programming and associate category to this function programming language L I denoted by CL. What are the objects of this category CL? So objects are data types of L. Data types of L. So we know that if we want to perform a programming, then we must have certain data, and then I should have some computable functions so that I could apply those functions to the given data to construct a program. So given any two programs, given any two data types x and y, so home xy, or you can say the arrow set of this xy is what, or the it is the set of computable functions of L. Okay, computable functions of L. So functions of computable functions are precisely, they are of this form. They are processes, procedures, procedures. Okay, so first we process, then we procedure, and then we have programs. Okay, so how do I define the composition of arrows? Suppose I have a data type x, a data type y, so I have a computable function f from x to y. So what does this computable computable function do? It applies on this data type x to give a data type y. So x here is called the input, y is the output, and from y to z, say I have g. Now g composition f is what? G composition f is actually applying g to the output of f. So applying g, the function g, to the output of f, to the output of f. So in computer theoretic language, this g composition f is actually written in this fashion: f semicolon g dot. Means I have applied g to the output of f. Now identities are what? Identity is doing nothing to this program. Means doing nothing. This program stays as it was. So the identity on this data type x is the doing nothing, is the doing nothing program. So now associativity of composition is trivial. Okay, suppose I have x to y computable function f, y to z computable function g, and say z to w I have another function or arrow h. So first I would take g composition f, means I would apply g to the output of f, and then to the whole output I would apply h. It is same as it is. So this is what this thing is: h composed with g composed with f. It is same as first I apply f from here to here to get the output, and then to the output of f I apply the function g composition f. So this is what, this is h composed with g, this is h composed with g. So it is same as, so this thing and this thing, they are same. So therefore from x to w, From this data type to this data type, I would get the same program whether I apply first this G composed F and then H, or first I apply the function H composed G. No, first I apply the function F and then apply H composed G. Okay, so the composition here is associative. And identities act as identities because doing nothing is actually, so if I have from X to X, that is identity on X, so this function does nothing to this program. So I was at the same stage by applying this function to this data type X. So again I have to apply a fresh F to this X to go to Y. So F composed with identity on X is F. Similarly, identity on Y composed with F is F. So this category is called as the category of programming, functional programming language. Okay, so these were some of the examples. We discussed some examples of finite categories. We also discussed some examples of, one example from logic and the other example from computer science. Now I would discuss some more interesting examples, and these are actually called as constructions on categories. Construction means I can construct categories from the given set of categories. So in the first lecture we also came to know about such type of example, and what was that? It was actually the product of the categories. So given two categories, I can construct their product. Similarly, I can construct more categories from a given category. So construction on categories. Construction on categories. So in the first, I think in the first lecture, I give you this example that suppose I have a category C and I have a category D. So I can form the product category C cross D. Okay, C cross D. What are the objects of this category C cross D? So objects of C cross D is what? They are actually pairs C comma D, where this C is an object of the category C and D is an object of the category D. So C belongs to category C, D belongs to the category D. And given any two objects, so pair of objects C comma D and then C dash comma D dash. So what is the home set? So home set is actually this one. So home